Chapter 2 deals with chemistry. Some of you love chemistry, some of you hate it. I presume some of you have taken chemistry already and some of you have not taken it since high school. So the first part of this chapter will be a review of some basic chemistry, and then we're going to move on to look at the biochemical substances that are important for the body. The first concept you need to understand is that matter, which remember is defined as anything that has mass and occupies space. So matter is something that we can feel, we can see. It has physical properties to it. So matter comes, for our purpose in the body, in three different forms. So it comes in solid, and it comes in liquid, and gas forms. Solid, liquid, and gas. These are said to be the states of matter. Now I know that your chemistry text has now said that there's number 4, plasma, but we don't find that in the human body as far as plasma matter. Now we find blood plasma, which is completely different. So we're not even going to talk about that one. Now energy, on the other hand, is something that does work, and it takes the matter and it does something with it. So energy does not have mass. We don't physically see it. We can see the effects of it. So it's kind of like the wind. We don't see the wind, but we can see trees blowing or hair moving. Energy comes in 4 different states or 4 different forms that we talk about with the human body. So it comes in chemical form. Chemical form would be stored in bonds such as ATP, which is the major. Totally got that backwards there. Hang on. ATP, which is the major energy source molecule for the body. It also comes in electrical form. So electrical form is going to be used heavily by the nervous system and by all systems, really. So movement of charged particles. Mechanical energy, which is defined as energy that moves matter. So the muscular system is obviously very important there. And then we have radiant or electromagnetic energy. So this is energy that travels in waves, such as heat or visible light or ultraviolet radiation, X-rays. These things all have an effect on the body, and they are felt by the body in some way. So obviously heat is felt. Visible light is detected by the retinas of the eyes. Ultraviolet light can burn our skin, and X-rays are absorbed into body tissue. Well, some body tissues, as you may know. So you guys have probably all seen a chart that looks like this. This is the periodic table for elements. And the periodic table, obviously for this class, you guys don't have to know much about this, but there are elements listed on this chart. So each one of the letters that you see represents a certain atom and a certain element. So the important ones that we look at for the human body and for biochemistry are your carbon, okay, your oxygen, your hydrogen, and your nitrogen. So these 4 make up the top 4 found in the body, starting with oxygen. Okay, so those 4 are important. Actually, if we're putting them in order, carbon should go second if you're looking at the actual percentage of the body mass. So, but these are the top 4, and then we have other ones that are going to be found in lesser, so such as calcium, which is found down here, sodium, potassium, even magnesium. So many of these different elements are going to be found in our body. We also have trace amounts. So some of the other elements, such as tin or selenium, even things like cobalt and copper. So some of the more heavy metals are found in very small trace elements in the body. Atoms are composed of three particles. You have your protons, you have your electrons, and you have your neutrons. Remember that each one of these carries, well, two of them carry a charge. So protons carry a positive charge, neutrons carry a neutral charge, and electrons carry a negative charge. So we see that the protons and the neutrons are found inside what's called the nucleus of the cell, of the atom. And then the electrons are all found in the outside, kind of moving around. So remember that they don't stay stationary. They move around. We kind of freeze frame it here. This is called the planetary model, where we can actually see the electrons, whereas in real life what it looks like is just a big cloud. So it looks just like a big cloud of electrons around the outside. Because they're moving so fast, it's hard to actually pinpoint just one. Your text goes on to talk about different terms such as atomic number, mass number, isotopes, and atomic weight. I don't care that you guys remember these for me, but on the final exam there's been a question about isotopes before. Okay, remember that an isotope has a different number of neutrons. Than would say the same element in its normal state. And this is what makes, if you guys have heard of like radioactive elements, typically they are isotopes. The next two terms, molecules and compounds, are different in that molecules is just a general term for two or more atoms. Any atoms, they can be the same or they can be different, whereas a compound is a more specific type of molecule that has two or more different types of atoms. So, for instance, if we were looking at O2, that would be a molecule, whereas CO2 would be a compound, a molecular compound. The next section talks about chemical bonds. Remember that chemical bonds are just relationships or attractions. They are not actual physical bonds. So when you see like something that looks like this, there is no actual piece that's touching the two oxygen atoms. When we talk about bonds, it's important to look at electrons. And the first thing we need to remember is that electrons occupy what's called the electron shell, which is the number of electrons that the nucleus, surrounding the nucleus, the number of electrons held per what are called shells. Shell 1 has a max of 2, and 2 and 3, remember, are increasing, so shell 2 can hold 8, and 3 can hold up to 18. So this is not really important to know at this point. What you need to remember is this about the ionic, covalent, and hydrogen bonds. The octet rule, remember that atoms desire 8 electrons in their valence shell. So when we talk about an ionic bond, typically what's happening is we have an electron that's being transferred. Okay, transferred from one element to another. So the example given in your book, and you can look in your book, is sodium. Okay, sodium chloride, which is obviously table salt. And when you look at sodium in its natural state, it has 1 valence electron, whereas chlorine has 7. So what happens is this 1 electron comes over here and is transferred, which then gives the sodium a positive charge and the chlorine a negative charge, and thus they're attracted because of their opposite polarity. The second type of bond is a covalent bond. In a covalent bond, elements will share electrons. An example of this would be oxygen, which has 6 molecules each by itself. You don't really find oxygen in its natural state like this. So when you put these two together, you get an oxygen molecule that actually shares 4 2 oxygen molecule, or atoms I should say, that share 4 electrons, which is why when you write O2, it has typically 2 lines indicating that it's sharing 4 electrons. So sharing. So the buzzwords here are transfer and share. The last type of bond is a hydrogen bond, and a hydrogen bond is more of an attraction. Okay, an attraction. So specifically we'll look at, say, water. Water itself, all by itself, if you just draw a molecule of water, remember, has a bent, so it looks like this, has a bent shape because of the electromagnetivity of the oxygen. The electrons as such, so we have, remember, 2 in here. So the electrons generally reside more around the oxygen, whereas the protons of the hydrogens are more exposed. Protons carry what kind of charge? Do you remember? So you should be thinking positive. Therefore, there's a partial positive charge down here. Partial positive charge. And since most of the electrons are residing up here, there's going to be a partial negative charge closer to the oxygen. So that if then I were to take a second molecule of water and put it into this scenario, the oxygen, which has a partially negative charge, would go nearer the hydrogen, and its hydrogens will be facing away. If I were to put another one up here, the hydrogen would go closer to the oxygen, so on and so forth. These dotted lines represent the hydrogen bond, which you'll see this in your text as well. Anywhere you see a dotted line in a drawing of compounds indicates that it is a hydrogen bond. And this is what contributes to certain aspects of water, such as its high surface tension. So you guys might know that water is considered to be a very hard surface. If you ever jumped into water or landed funny on it, you would know that it did hurt. Okay, so high surface tension, it has a high boiling point. Okay, and it has properties about freezing, such as when you freeze water and put it into its liquid, it floats. This is actually not normal for most elements in liquid form. When you put a solid into a liquid form of an element, usually it will sink to the bottom. Water, however, floats because it's less dense due to the hydrogen bonding. Chemical equations are important in regard to knowing how things are going to react and what they are going to produce. So when we look at a chemical reaction, so something that's either formed or broken apart, these reactions are written as what's called a chemical equation, containing on one side of the equation the reactants, which are what you're putting into it, and the products on the other side, which are the resulting end products. If you've taken chemistry, you know they have to be balanced, so you have to start and end with a certain or a specific number. You can't all of a sudden change the number. These are compounds are typically represented as molecular formulas. So when you see something like this, C6H12O6, okay, that might just look like a bunch of mumbo jumbo, but this is glucose. This is the molecular formula for glucose, and you guys have all seen, you know, H2O, CO2, those types of things. These molecular formulas indicate how many atoms are joined by bonds and how many are maybe freely, so free atoms. There are different types of chemical reactions. So you see different types of chemical reactions. So you have a synthesis, which is building something. You have decomposition, which is breaking something apart. And you also have exchange, where things are being made and broken, kind of switching places. Now, when we look at reactions, it's important to note what's called a redox reaction. This stands for reduction, oxidation. Reduction, oxidation. And this is important for the gain and the losing of electrons in certain molecular compounds. So redox reactions is important to know. We'll talk about these at a later date. Also important are the rates of reaction. So there are really three things that can speed up a chemical reaction. Number one is the temperature. What do you think you will do to the temperature to increase the rate of the reaction? We're going to increase the temperature. Number two is the concentration. Okay, concentration. If you increase the concentration, there's a better chance that you will have collisions of molecules, thus more reactions. And number three, the particle size. What do you think about size? Do you think bigger or smaller particles will move faster and have a higher rate? Okay, it's going to be smaller particle size. So smaller particles, higher concentration, higher temperature, these things all speed up chemical reactions. Another thing that speeds up a reaction is a catalyst. Okay, catalyst is a compound that is added to a chemical equation or added to a reaction that does not change or become part of the product. So it does not interfere with what is happening in the specific reaction. In the human body and in nature, we call a biological catalyst an enzyme. You guys have all heard of enzymes. Okay, enzymes are what we will call them from now on. We're not really going to call them catalysts, but remember what they are is that they are substances that speed up a reaction. Could you imagine if you ate a meal and the meal went into your stomach and the stomach didn't add anything to it, it just churned it over and over and over and didn't add in all of the secretions? How long do you think it would take for a piece of meat to digest inside of your stomach without enzymes? So enzymes are obviously very important for the digestive system and for other systems in the body. This concludes the first part of the chemistry show me. The second part will be coming soon, so please check back for the biochemistry portion.